I mentioned earlier that carbon monoxide is generated as a result of incomplete combustion. Not all of the carbon in the fuel bonds to two oxygen molecules. Instead, some of it only bonds to one. Let's get into some more specific scenarios that can cause this to happen. There are three broad categories of situations that can result in incomplete combustion. The first is a fuel-air mixture that's rich, meaning that there's not enough air present to completely burn all of the fuel. The second scenario is poor mixing. There may be plenty of air present, but it's not thoroughly mixed with the fuel, so there are pockets of fuel that don't get enough air. The third scenario is a flame that's too cool, making it difficult for the carbon to bond to the second oxygen molecule. The first scenario, a rich fuel-to-air mixture, can result from several problems. One is simply that too much fuel is being fed into the burner. This can happen with either gas or oil. Another is that not enough air is being fed into the burner to mix with the fuel before it's ignited. We call this primary air. There are several reasons that this can happen. The last cause of a rich mixture is that not enough secondary air is being supplied around the flames to guarantee complete combustion, and there are several possible causes of this. So let's dig further into each of these possibilities. We'll start by exploring the problem of excess fuel flow a little deeper. For oil-fired appliances, this is usually caused by an improperly sized nozzle. Nozzles are replaced as a matter of routine maintenance in oil appliances. They can be purchased in a wide variety of flow rates, since appliances with higher heat output require a greater oil flow rate. In fact, it's possible to calculate the proper size of the nozzle. When a gallon of oil burns, it gives off about 140,000 BTUs of heat. So if a boiler is rated to have an input capacity of 100,000 BTUs per hour, then it needs to supply 100,000 divided by 140,000, or about 0.71 gallons of oil to the burner every hour. So a nozzle rated at 3/4 of a gallon per hour, or GPH, would be suitable. If instead a 1 gallon per hour nozzle was installed, the carbon monoxide generation would probably be high, unless adjustments were made to proportionally increase the airflow as well. There might also be soot in the combustion chamber from fuel that didn't burn at all. For gas-fired appliances, the fuel flow rate is determined by two factors: the gas pressure and the size of the orifices the gas flows through to enter the burner. The orifices don't often get changed, but the gas pressure is adjustable, and it's frequently a problem. The easiest way to determine whether the gas flow rate is a problem is to use a stopwatch to measure the gas flow rate through the meter. The process is fairly simple. First, turn off all of the gas appliances in the building. Then turn on only the one having the carbon monoxide generation problem. At this point, you know that any gas flowing through the meter must be going to that appliance. Now go to the meter. There will be multiple dials with needles spinning inside them like a clock. The one spinning the fastest will be measuring the smallest increment of gas flow. In single-family homes, it's usually either a half a cubic foot or 1 cubic foot per rotation. In commercial buildings, the volumes will be higher. So every time that needle makes one full rotation, that amount of gas has flowed through it to the appliance that's running. Use a stopwatch to measure the time it takes for one rotation of that smallest dial. Now you can scale up that measurement to how many cubic feet would be flowing to the appliance if it ran for a full hour. The number of cubic feet per hour, or CFH, is equal to the dial size in cubic feet per revolution times 3,600 divided by the number of seconds it takes for one revolution. Now a cubic foot of gas contains about 1,000 BTUs of heat, so the actual input to the appliance is approximately 1,000 times the cubic feet per hour that was calculated. You can get more accurate than this by looking at the gas bill to see the precise BTU content of the local fuel supply, but approximating it as 1,000 BTUs per cubic foot is usually close enough. Let's look at an example. A house has a furnace that's generating too much carbon monoxide. We look at the meter, and the smallest dial is a half a cubic foot per rotation. So we turn off all the other gas appliances in the house and turn on the furnace. We time it, and it takes 19 seconds for one full rotation of that smallest dial. Next, we plug the numbers into the equation. We multiply the dial size of a half a cubic foot per revolution times 3600, then divide by the rotation time of 19 seconds. The result is a gas flow rate of just under 95 cubic feet per hour. Since every cubic foot of gas contains about 1,000 BTUs, that means that about 95,000 BTUs per hour of gas is flowing to the appliance. If we look at the data plate on the furnace, and it states that the input capacity is 80,000 BTUs per hour, we know that the flow rate is significantly higher than it should be, and this might be the cause of the high carbon monoxide generation. If the fuel flow rate is correct, it's still possible to have a rich mixture if there's not an adequate supply of air to the burner. Burners are designed to draw in air at the same time that the fuel flows through them. And this air that mixes with the fuel before it's ignited is called primary air. If the flow of primary air is somehow restricted, carbon monoxide can be generated. On many newer appliances, the primary air flow rate is fixed by the burner design. But on most older appliances, there are shutters that allow it to be adjusted. If they're not properly set, the result can be a rich fuel mixture. It's also possible that the burner tubes can get blocked. One possibility is spiders and other insects getting inside them. The obstruction won't slow the fuel flow rate down, but it will restrict the airflow, resulting in a rich mixture. In addition to primary air, appliances draw in air to mix with the flames after they've been ignited. This is called secondary air, and it helps to ensure that every carbon molecule is exposed to plenty of oxygen. The secondary air is actually drawn into the combustion chamber by either the chimney draft or the suction of an inducer fan. It's helpful to think of the entire system as one long tube, from the burner through the heat exchanger and out of the house through the chimney or flue pipe. So if the draft out of the flue is weak, then the flow of combustion air into the combustion chamber will also be low, and carbon monoxide could result. In addition to draft or inducer fan problems, insufficient secondary air can be caused by obstructions blocking the air inlets on the cabinet or door of the appliance. Another possibility is that the space the appliance is located in is too small or too tightly sealed to feed enough air to the burners. Even if there's adequate air supplied to an appliance, carbon monoxide can still be generated if it doesn't get mixed well enough with the fuel and with the flames. The most common cause of poor mixing is burner ports that are obstructed with rust and scale. Another cause is a damaged burner tube. The third scenario that can cause carbon monoxide to be generated is a flame that's too cool. Quite a bit of energy must be available to create the bond between a carbon atom and a second oxygen atom to form carbon dioxide. If there's not enough heat, then the reaction will stop with some of the carbon only bound to one oxygen. In some cases, there may be a visual indication that this is happening. As the image on the screen shows, a very hot flame will emit blue light. A cooler flame will become more white and yellow. So ideally, when we observe flames, they'll be blue. Yellow tips can be okay. The combustion gases start to cool as they move away from the point of ignition, but flames that are substantially yellow can be an indication of problems. This is not a definitive way of diagnosing carbon monoxide generation, but it can be a useful clue. So, what will make the flame burn cooler than it should? Well, several problems can do it. One is a cracked heat exchanger. The heat exchanger separates the combustion gases from the building air in forced air systems. If a crack develops in the heat exchanger, then the building air can blow into the combustion chamber, disrupting and cooling the flames. Another potential problem is too much primary air. It may at first seem counterintuitive that too much air would result in carbon monoxide production, but it can happen. The air that enters the burner is cool, so if there's far too much of it, it can force the fuel-air mixture to flow through the burner too quickly and cool off before the components have a chance to complete the combustion reaction and form carbon dioxide. Another problem that can cool the flame is impingement, which simply means that the flame is contacting a nearby cool surface rather than just floating out in the air. If the flame touches a surface, that surface will absorb heat from the gases, stopping them from completing the combustion reaction. The circumstances of the combustion reaction in natural gas systems is largely fixed by the system design. Especially in newer systems, there isn't much that technicians can change. But in oil-fired appliances, the operation is greatly affected by the choices and adjustments the technician makes in setting up and maintaining the system. Every oil technician should use a flue gas analyzer when completing service to ensure that any adjustments made haven't caused a spike in carbon monoxide production. Typical tasks that can affect CO production include replacing the oil nozzle, adjusting the position of the air intake shutters, modifying the draft by adjusting the barometric damper, and cleaning or not cleaning the soot that's collected on the heat exchanger or the walls of the combustion chamber.